So, welcome everybody on the second part of our summer season of seminars. This is the Prague seminar for mathematical physics, and as you noticed, we had a short delay, for which we apologize, and we can somehow delight you by stating that next to me, Carlo Cremonini is standing and is prepared for giving us his talk. The talk title is Forms in Supergeometry, Application in Physics, and all that. But this could be stated in various ways, as Carlo told me, because we can expect quite a longer journey seeing him near the blackboard. This is the first of this continuing talks by Carlo, and he's a new postdoc researcher in Mathematical Institute of Charles University, and we are very glad he give us a chance to hear something about this topic. So, Carlos, the floor is yours.
Thank you for the introduction. Thanks. And thanks also to Milano for asking me to give this series of talk. Well, so the goal of these talks will be to give a very practical introduction, very practical explanation of how to deal with differential forms on supermanifolds and how to use them in some, at least, physical context. So I will start today by talking about forms in physics, and I will follow mainly Witten's approach, a recent paper by Witten. Well, actually, he was not the first to treat forms like this, but I refer to that paper, and then I will continue the discussions trying to touch some physical context like supergravity, like Chern-Simons theory, and homotopy algebras, and the end of this series will be what I'm currently working on, so Lie superalgebras and maybe their application to brains. Okay, so let's start with the basics. So what is a supermanifold? Well, we can define supermanifold as we can do for other kind of varieties. So as a ring space, so we have a topological space equipped with a certain sheaf of functions, and in particular we can define the space R/P/Q, where these numbers count the number of bosonic dimension and fermionic dimension respectively, as the space defined by the topological space Rp, and the functions, the C infinity functions, for example, I will state in the real environment, equipped with a certain Grassmann algebra. So with this, I mean that our functions locally will be functions on the coordinates, bosonic, which I will call x, and fermionic, which I will call theta, will admit an expansion like this. So we have a term purely bosonic, then a term which is linear in the thetas. I'm assuming the summed index convention, plus terms which contain higher powers of theta, up to the fp of x times theta 1, theta 2. Sorry. Okay, so these are the functions, and what is a supermanifold? So is a super ring space which locally looks like this. Okay, And so what are points on supermanifold? Points are locally described by a set of coordinates and like this. And but sometimes it could be difficult to visualize these as points because of an important coordinates. And for example, it is also difficult to have an interpretation of values of functions at certain point. For example, it is not difficult to see that if one consider fermionic functions, so odd functions, their consistent value is actually only 0. So there is a very, let's say, interesting way to give a meaning of points on supermanifold, which is actually inherited from algebraic geometry, which is called the functor of points. So actually, what one does with the functor of points is to parameterize the points of your supermanifold with an, let's say, an associated hidden supermanifold that gives you the parameterization of this point and their parity, so even and odd parity. So, but I'm not really familiar with this formalism, so I tell you what I got from the physical point of view. What does the functor point suggest from the physical point of view? Well, actually, it is the way to give meaning to odd functions. So in physics, we are used to say, let's consider an odd function, but how do we do it? Well, we assume that there is an unspecified underlying Grassmann algebra that actually characterizes the odd parity of the functions we are considering. This is the bottom line, the use in physics one has of functor of points, actually. Okay, so this is the definition of supermanifold. This is the local version, and given a supermanifold, we have that the odd coordinates generate an ideal important, and thanks to which we can define the base manifold, which is defined as the same topological space, but equipped with the functions defined by quotienting out the ideal generated by all the coordinates. Okay, so this is these are supermanifolds, and let's see how to define forms on supermanifolds.
Maybe just one clarification question. How do you define quotient of sheaves? It's defined by object-wise, or
by well, it's defined open-wise. So you quotient out the odd functions actually.
Yeah. So you firstly evaluate the sheaf on an
open set.
Open set,
and then you project
just
out.
Yeah, to take the quotient.
Yeah, exactly.
And define it for any such open set.
Exactly.
Okay.
Exactly. And in this case, the base manifold, the reduced manifold, actually reduces to a usual smooth manifold. If I write here, it is readable, or there is a shade.
I hope so.
Okay. So let's now see what are forms on supermanifold when we can do the usual construction of forms we have on any given manifold. So we construct the cochain complex of the Dirac differential. Here we have this, we have 1, 2, etc., where these spaces are locally generated by the differential dxi and d theta alpha with the following properties. Well, the dx's, as usual, are taken to be odd, so they anti-commute, while the d thetas are taken to be even, so they commute both among them. And with the dx's. Okay, so these are the local generators of this space, and all the others are simply considered by taking graded symmetrized tensor products of this. So what we immediately see is that because of this property, so the theta's commute, and in particular they do not square to 0. They do not square to 0. The complex of forms of what we call superforms on a supermanifold is not bounded from above. So it never comes to an end. So immediately late in the 70s, 80s, there was the question, so I do not have a top space, and in particular, I do not have a space on which I could integrate forms, differential forms. So what are the objects that should be integrated on supermanifolds? Well, these objects were defined first by Bernstein latest and are called the integral, or maybe better, integrable forms. And so they're defined in this way. One locally introduces this space, the Berezinian space of your supermanifold, that locally can be written like this. You take the product of all the odd generators of the tangent and cotangent spaces. So this is the object you call the Berezinian space. The product locally, the product of all the odd objects, so the dx's from the cotangent space and the derivatives along the theta direction from the tangent space. And this is the space you call the Berezinian, because actually if you take transformations, coordinate transformation of this space, you can see that this transforms actually as a Berezinian of the matrix transformation, or the superdeterminant. And out of this, you can construct the complex of integral forms, or integrable forms, in this way. You take the Berezinian of your supermanifold and tensor it with graded symmetric powers of the parity reversed tangent sheet. This is and the tensor product is made of on the sheet of functions, and this is how you define integral forms. So there are tensor product of parity change vector fields with values in the Berezinian model, and you can construct a chain complex out of this by introducing the differential. And I took this, all these things may be found in any textbook, in any paper. I used, for example, also the book by Manning, which is a very good introduction to supermanifolds. And the differential reads like this. You have a right derivative along the vector field ZA, where with Z I indicate both x's thetas times the derivative with respect to the parity change vector field. Okay, with some sign. This is the differential. It is possible to verify that this object is important, and thanks to this, you can construct the cochain complex of integrable forms in this way. You take the Berezinian, and you obtain all the integrable forms. Sorry. So on, acting with this differential. Okay, so notice immediately that as for the same reasons for which the complex of differential forms is unbounded from above, the complex of integrable forms is unbounded from below, exactly because you can always, in this space, the parity chain vector fields, you have both even and odd objects. So you can construct a divitum any space by simply taking powers, graded symmetric powers of this space. Okay, but I will now describe another realization of the Brazilian space of integrable forms, which is, in my opinion, much more useful and much more powerful for computations and then for physics applications. And as this approximate title claims here, is made out of those which will be called delta forms. So again, now for this construction, I will follow Witten's paper. So he starts by taking, let's consider the Clifford algebra defined in this way. So this is better to write like this. Okay, so we have, these are the usual odd forms we have on a manifold, and with this I indicate the contraction operator, or if you prefer, I can write it like this, and this forms a Clifford algebra. So the question is, which modules can I construct from this Clifford algebra? Okay, I'm doing just a quantum mechanical way of thinking. So I can construct all the, let me call them particle from this Clifford algebra in two ways, for example. So let's consider a state that I will indicate like this, which is defined by this every time. So how should I realize this state? One way to realize this is, for example, by saying this is on state 1. And how do I construct my particles out of this? Well, I simply take products of the dx's of on these states, and then any product up to the maximal number of dx's I have in my Clifford algebra. But so in this case, I thought these the contraction as a destruction operator, annihilator operator, and the dx as creator operator. But actually, I can construct it for a different state, which I indicate like this, which is defined by this. So now I switch the names, the interpretation of annihilation and creator operators. So how could I realize this? By remembering the odd nature of the x's, I could say that this is the determinant, or if you prefer, the product of all the x's. Actually, this is 0, again, because of the odd nature of the x's. And then I can construct all the other states of this theory by adding contraction on what?
Sorry, there is an echo.
No, nemáš uklízet, alebo bývá konec. Ano, určitě.
Should I go?
Ne, tam je, jako tam nějakou zla.
Sorry, I believe you are muted.
Sorry?
Yeah. Is it fine for that moment?
Yeah, it's fine. Thank you.
Okay. Okay. Instead of Clifford algebra, I can construct now a Weyl algebra, which is, yes, contraction and d theta. Okay, now these are commutators, not supercommutators, because these objects, this one is simply the derivative with respect to d theta. And these objects they're both even. So now I don't have a Clifford algebra, but a Weil algebra, and I can construct the space of my particles exactly in the same way I was thinking before. So I first define down state by saying it is annihilated. So I call these operators annihilators, and I construct this space like this. And so again, I have this space is can be realized as this simply, and all the other states are constructed by acting with the creator operator on this. But now I can create particle without any limit, because now these objects are even, so I can take any power of them. On the other hand, I could define the state which is annihilated by the other operator. And so, again, I switch the role of the creator annihilation operators. And how can I realize this? Well, this is a multiplicative operator, an even multiplicative operator. So one way to realize this is by saying that this state is constructed by the Dirac delta, the formal Dirac delta, the product of the formal Dirac deltas of all these even coordinates. Obviously, I'm claiming the property of d theta delta of d theta equal 0. So this algebraic formal property. And now, again, starting from this state, since these are formal partial distribution, they can be derived to any power, and in this sense, this is simply the derivative operation, acting on delta, and all the states of this module are constructed by acting with derivatives on this. What is the main difference between what we had before, the Clifford algebra, and now the Weil algebra? Well, I cannot move in this way, at least, from one state to the other, because acting here with the creation operators, I will never get an object like this and vice versa. So these are two really different modules. And this is an alternative realization of what I was talking about, the Berezinian module. So now I want to use this physical, let's say this physical realization of integral forms and write my Berezinian module as like this. Now I add also the usual coordinate, the x coordinates. So my Berezinian on a given supermanifold will now read like the product of all the x's, and the product, I will use the wedge symbol as well, of all these Dirac deltas. So this is now the realization of my Berezinian module, and the integral or integrable forms I construct out of this are made in this way with the Berezinian. And remember, before I had the parity changed vector fields, tensor the Berezinian. Now, what does this mean in this realization? Parity change vector fields is nothing more than contractions operators. Contraction both in the even and in the other direction, contractions with some index acting on the Berezinian, which is realized in this way. And then all the other spaces are constructed from this point of view by acting with other contractions. And the dictionary from the previous definition is really immediate. You change the realization of your Berezinian, but the definition of integrable forms is exactly the same. What is an advantage of this? is, for example, here in this way of thinking, in this while algebra, you can introduce a differential, the drum differential, which locally reads. I am omitting the x coordinates. Sorry. This one, and you can use this differential both for this module, the superform module, and for this module. You have only to recall the properties you are claiming for these deltas. So, in this realization, which is one of the advantages that you are using here, exactly the usual Dirac differential you have on superforms, which is bipotent and whatever. And so this is one of the main advantages of this, because since you're using the Dirac differential and these formal rules, actually all the other constructions you have from Cartan geometry are immediately inherited. So the derivative, you can write it using Cartan formula and whatever. Okay, so these are the objects which I call delta forms. And so they are equipped with these properties. I claim that their parity is 1, so I give them an odd nature. And this is because exactly for the same reason for which I give another nature to the dx's, because I want the integration to be oriented, or in some sense, I want that the product of all these dx's reproduces exactly the determinant. Here, I give the deltas this property because I want that the product of all these objects reproduce the Bernoulli super determinant. Then I have this property, d theta equals 0. Then I have this is simply the Weil algebra property. So if we have d theta acting on a certain derivation of our delta, a certain derivative of our delta, this gives simply minus n contraction n minus 1 of the delta. And you can see it both using the Weil structure or by simply integration by part. This is the integration by part, it's nothing more. Okay, and see, because of this assignment parity, you also have that the usual rescaling rule of the Dirac delta comes in this way without an absolute value. Usually I should put an absolute value here, but because of this assignment, it turns out that the consistent way of rescaling is without it. Okay, so these are the objects I will call integral forms, and as a very, very quick exercise, I want to show how to deal with them and why do I claim that with this object I can construct the Bernoulli shift. So actually an object that transforms like a Bernoulli. So let's take the very easy example of R11. So we have just one even and one odd coordinate. So in our case here, the Bernoulli is written like dx delta of d theta. Let's now take a change of coordinates like this. So we have here a super matrix acting on this. So we have d theta. And so these objects become a dx plus alpha d theta and beta dx plus b theta. So let's study the transformation property of this object. Well, we have the Bernoulli goes to ADX plus alpha b theta times Dirac delta of b d theta plus beta dx. Okay, now I simply use those properties of the delta to show that this object transforms correctly. So I can take a b out of this delta by using the scaling property. So I can do like this, and the b goes at the denominator. Then here I can use both the fact that, well, I'm using a delta, so I'm thinking of it as an object which has support on the zero of this argument. So I could say d theta equals formally to minus beta or btx. Or otherwise, I could take this object and tailor expand it, but this expansion would be truncated immediately because both beta and the x they're odd. And it's equivalent which way I choose, and insert it. For example, inserting this expression here, I get a dx minus alpha. Let me write it like this: -1 beta dx or over b, okay, sorry, and times delta of d theta plus beta over b dx. But now this first part, this first term is proportional to the x, which is odd, then this object drops, and in the same way I could have seen this by Taylor expansion. So what I get is a coefficient which is a minus alpha b minus 1 beta over b times dx delta of the theta, and which is exactly the superdeterminant of this supermatrix times the Brazilian. So this is exactly the way you work with these objects, and the way to see that actually they define correctly an object transforming as a superdeterminant. It's not difficult to generalize it with to any dimension. I will only have to take care of antisymmetrizations. Okay, great. So, well, where does this formulation of integral forms comes from? Comes from physics, from in particular superstring theory, and the procedure of which is called the Bottomization. In particular, when doing with the superstring perturbation theory, one comes to the problem of integrating on supermoduli space, and then one has to take care of certain insertions that that are used to correctly define an integration, both on even and odd coordinates. And what you do in doing superstrings with the Bottomization procedure is actually to introduce those Dirac delta forms. Okay, so starting from the Weyl algebra, you have also another possibility. This is our algebra. So we constructed the top state, which is actually the Brazilian. We constructed the down state, which is actually constants from which we define the complex of superfolds, but we can also define an intermediate state. Let's call it like this. And you claim that this object is annihilated by some, by the multiplication by some d thetas and by the contraction on, let's say, let's formally write like this, along the other directions. Okay, so you simply say that along some direction, these are the annihilators, and along the other directions, these are the annihilators. So which are the states, which is the state you construct like this? Take, for example, a simple case where we have simple two directions. So we take, for example, the theta 1 here and contraction in the direction 2 here. So which is the state generated in this way? Well, it is actually simply, if you want, 1 times the Dirac delta along the theta 1 direction. So this is an object which does not have the maximal number of Dirac deltas because it is a compactly supported distribution only on this direction. In the other direction, you simply do not add nothing. These intermediate states are called usually the pseudoforms, and they are a very, very rich construction, but a very not well-defined construction, because okay, let's see which is the main problem when dealing with this object. Well, okay, we can take a transformation, a basis transformation of the coordinates, and consider, for example, this object here. What is the meaning of this object? Well, for example, as I said before, I can Taylor expand this, so I will have some to a given power times, right, like this, contraction 1 with the power n acting on the delta of the theta 1. So immediately we see that under coordinate transformation, these objects do not behave well, they do not transform linearly. They're not tensors. So they up to now have only a local realization. And another way to see this is, for example, consider at a given form number, let's say consider form number 1, the space equipped with this object, which are the generators of the space? Well, I indicate this space like this, form number 1/1. This means that is called from physics the picture number, and it simply counts the number of deltas you have in your space. So which are the generators of this space? Well, you have a single delta, but you also have, for example, the object constructed like this, the theta 2 contraction 1 of delta, and so on. The theta 2 to any power, contraction 1 to the same power, because this object counts like form number +1, and the contraction counts like form number -1. So this will have always form number 0 acting on it, and so on. So you immediately see that this space, these spaces for any form number, they are not finitely generated. So in other words, these deltas, they are not finite dimensional representations, and this will come to be very important in the following lecture, maybe, or whenever, when talking about the superalgebras and their cohomologies, because we will show that it's possible to find cohomology classes in these spaces that, in the case of Lie algebras, will be well defined, not ill-defined like this, but admitting the possibility to look for infinite dimensional representations. Okay, so as we've seen before, it is not possible, here, it is not possible to move from superforms to integral forms by simply using the Witten algebra. So, which is the instrument that I can use to move from one complex to the other? Again, inherited from physics, from superstring theory, we have what are called the picture changing operators. These are operators that exactly do what their name claims. So they allow you to change your picture, in the sense they allow you to move from superforms to integral forms and vice versa. They have a very huge applicability in physics, and I hope we can see some of their applications. So this object, you have again here the complex superforms. And here you have the complex of integral forms. And feature changing operators are operators that allow you to move in these directions. In this way, by raising the picture number by using the same terminology from string theory, you have the operator y, and in the other direction, you have the operator z, and they are quasi one inverse of the other in the sense that we are going to describe, and which is a characterization of these operators. Well, a local characterization of the operator epsilon is obtained by taking the product of all the coordinates, the odd coordinates, and all the Dirac deltas. This is what you call the picture raising operator. As you see, it is a multiplicative operator and simply takes a form living in this complex and stick to it those Dirac deltas, the picture number actually. And it is a cohomology class, it is a cohomology representative, so it is very easy to see that the drum differential of this object is 0 simply because of the properties of the Dirac deltas, and it is not exact. It is not exact. So this is again a property you require from superstrings to this operator, because in superstrings your operator is not the drum differential, but it is the Bierstein differential, and the fact that this object is a cohomology class is simply saying that it won't modify the physical degrees of freedom of the object you were starting with. Vice versa, the other operator, the operator Z, has the same properties. It is a cohomological operator, so it will not modify the number of physical degrees of freedom. Okay, the operator Z is defined this way. It is a formal way to define, again, simply taken by superstring theory. By take the graded commutator of the drum differential and the heaviside distribution along a contraction, which is defined formally by its Fourier transform, and you can simply see that acting with these kind of operators on integral forms, then you can move from here to here. So again, you start with an integral form. This object removes the deltas actually and gives you as an answer an integral form, superform. So, and these two operators, they are inverse in the sense that it holds this equation and this one. They're not really inverse one another because they both have a kernel, as you can immediately see from here. For example, by choosing this representative, again, these are cohomology classes, so I can take any representative in this cohomology class. But for example, by choosing this one, I see that any object which has a direction in the which has a contribution from the other direction, which will be projected out. So they are not inverse, but they are inverse in this sense, since they both the operators they both have a kernel. Okay, and
explain me in more detail how the heuristic function works.
What, sorry?
How the heuristic?
Oh, sure.
Cannot somehow see.
Yeah, I can see it if you want in an example. Okay. Well, you can consider you first define this, let's say, in a given direction. In a given direction, alpha through is a Fourier transform. So you take minus I, the epsilon equal to 0 of an integral of R or given integration variable, and here you have t plus I epsilon e to the power of I t contraction. This is the Fourier representation of this object. And how do you work with this? Well, let's see. let's act, for example, on a single Dirac delta. Well, this, since the contraction operator for the Dirac delta is a derivative, this is simply a shift operator. So this means delta of beta alpha plus alpha t. Then now you can use the Dirac delta to perform this integration. So you first pull out the I, so you have minus I delta of t plus beta alpha over I. Then you are integrating, you are putting t equal to beta alpha over I and inserting this here. And what you obtain in the end of the day is I over d theta alpha. I was not doing this example because what you're obtaining here is what is called an inverse form, which is another class of differential forms you can have in supermanifold or supermanifolds. These correspond in physics to what is called the large Hilbert space. So again, these these come from a dictionary you can have starting from superstring theory. But what is the main point is that your operator Z, which was defined by D and this heaviside theta, passes, since you are acting with this operator heaviside theta, passes through inverse form, so passes through the large inverse space. But the result of the operator Z will always be a conventional form, as super form. Or in physics, you say that this operator gives you a result in the large inverse space, but the Z operator gives you a result in the small Hilbert space. So the space, the Hilbert space you have, the usual Hilbert space you have. And the way to do that is that, for example, consider again the operator Z acting on, for example, the picture changing operator, and see in which sense they are inverse one another. Well, the part where the differential is on the right gives you trivial 0 because there is a cohomology class. So you first act with the operator theta, obtaining this result. So you have d of the theta over, no, sorry, I over the theta, it was, yeah, over the theta. Then you had here also minus I in the definition of the operator Z. Here the theta, this theta over the picture changing operator, minus I and I go out. The differential of the theta gives simply the theta, and so you take 1. So even though through calculation you had to consider this inverse form, or if you want the large inverse space, at the end of the day, what you get is a standard superform. So these operators are those that allow you to move in the from the superform to the integral form complex and vice versa, and which is their use in physics. Well, for example, well, in physics, obviously in superstring theory, I've already mentioned many uses when you have to integrate. These are exactly the insertions you have to put when doing superstring calculation theory in order to integrate on the supermoduli space. But let's say in classical super physics, so for example, let's say supergravity, which is a use of these operators. Maybe I should stop and start again next week.
But we somehow lately start with approximately 5
Maybe
minutes.
since
delay.
Eugene and we for another talk, maybe that would be good.
As you want. Okay. If it's not a problem for you, I
Not a problem.
Okay.
So thanks very much for your talk.
Thank you.
And,
Sorry, this was quite introductory, so
Good.
Okay.
Yeah. Okay.
Nice to warm up the audience. Or
Understandable.
Okay, hope so.
not um, despite understandable lecture, I encourage people to off your microphone and ask questions if there are any questions from online participants or. At the very beginning of your talk, you defined Berezinian. Was there any assumption on the orientability of your manifold?
Yeah. I'm assuming that the base manifold is orientable. Yeah. It's, sorry, I forgot to say that.
Yeah.
Yeah, thanks.
So, formally, we would go from super to gradient. What would kind of change?
So you mean that instead of having Z2, you have Z?
Yeah. Or maybe just positive or non-negative. But
I don't. You mean which kind of forms you should be able to use?
Yes.
I don't know. I don't
Because
know.
normally we just say you integrate, like, you have the 2 degree associated, and you write down essentially the Berezin integral.
So
you have the odd, you treat them like odd, and
even you did that even. Okay. So you mod the 2 association. Okay.
Yes, that's, I mean, if people write
Okay.
in textbooks,
But I don't know if in this case, actually, one, for example, could perform this linearly the construction of delta forms. Because if you have objects, for example, which have parity 2, would you be able to do that?
Well, then for parity 2, probably would use delta just for the odd ones. No?
Okay. No, but I mean that the corresponding form has parity 2. So you
yes,
start.
okay, yes.
Also, I don't know in that, because here you made heavy use of the parity changing operator, but in that case, you don't have a parity change. You may have shifts or things like that. I don't know how this would change the game.
Yeah.
And somehow modify your Berezinian construction in case of Z grading.
Well, maybe
because of the same issue we're struggling in Z2 grading.
Berezinian is kind of like Berezinian, it just
exactly in the same way.
Yeah.
You take whatever
you
can.
take whatever is odd, and you just even and find it.
Okay. Well, it should be interesting to check if this will be, let's say, compatible with the other more fundamental definition of the Berezinian, say, because the Berezinian can be introduced also in Manin's book, introduces it starting from Spencer complex and right modules and things like that. I don't know if this could go through. I actually don't know. Okay. Yes, I was actually asking that some days ago also to Eugenia.
So if there are no other questions, we thanks the speaker again.
Thank you.
Okay.